Good morning, everybody. I hope that you guys are having a good start to your day. I hope that you had a great weekend. Um, that's what I got. Today, what we are going to do is we are going to be talking about intermolecular forces. If you remember last time, one of the things that we were discussing was we were discussing basically like solutions and physical properties related to those things. If you remember intermolecular forces versus intramolecular forces, that's a really important thing for us to be working on in this kind of module or this block of material. Um, while I'm on that topic, I want you to know that we're going to have a couple of quiz homework assignment things posted to Canvas. They will be posted one today, one Wednesday, one Friday. They're all going to be due Sunday night at 11 p.m. You're going to have two attempts on them, and they're going to be short, two, three questions, maybe four questions tops. Um, and I'll go ahead and kind of as as is needed or as I'm able to, I'll get them up sooner rather than later. But today, what we're going to talk about, we got one question on the agenda today. We'll see what else we get out of this. So, intermolecular forces, kind of a continuation. So, our intra versus intermolecular forces. So, one way to think about this is if I were to give you a question that asked about what forces hold one water molecule together, I would want your answer to be intramolecular forces. If I said, what forces hold together, um, or what forces hold together a solution of water, then your answer would be intermolecular forces. So inter is between water molecules, and intra is within one water molecule. This is all an important thing to keep in mind with respect to what those are. So here we've got that nice depiction of inter versus intramolecular forces. Those two terms, inter and intra, are not interchangeable. It might be tempting to make them interchangeable, but don't fall into that trap. Now, with respect to that, and with respect to what I was just saying about, how do we define one thing or another, um, I think that it's helpful to think about this right here, this statement right here. The physical state depends on intermolecular forces. So surface tension of water is basically a result of the intermolecular forces. In addition to surface tension, boiling point, melting point, BP and MP are both dependent on intermolecular forces. Intramolecular forces do very little to influence that. Are they relevant? Yeah, they are. But when we think about a solution or a gas or lots of something put together, you want to be thinking about intermolecular forces as opposed to intramolecular forces. Um, so with that, got this nice video that shows kind of let me clear all my drawings. Pop this open. I believe that should keep the share there. I'm gonna pause it. Let's see. Yeah, good. So in the event that you've been to like I don't know, a Halloween carnival or something like that, this is probably something that you've seen, and that is dry ice, which is frozen. It is solid carbon dioxide. Solid carbon dioxide dropped into a glass of water. Well, here we go. Here's our solid chunk. You can see it's already beginning to transition phases. And boom, it begins transitioning very, very quickly. The reason is that because the temperature of that water is so high relative to that solid CO2 that it's just going to kind of bypass that liquid phase. This is what's known as sublimation. So here we see that subliming or that sublimation where we're transitioning from a solid to a gas. Now, what that means, and this is, to me, this is a very good test question. The bubbles that result, or if you drop and I'm trying to think of how I would phrase this kind of on the fly, but if you were to take solid CO2 and drop it into water, a solution of water, what is inside the bubbles that result? All of that bubbling up, what is that? And you can go ahead and add to the chat if you feel comfortable. I'll give it a couple of seconds. It's CO2. You're absolutely right. It's carbon dioxide. It's gaseous carbon dioxide. And you see that, and if you put your hand on the bottom of this beaker here, would it be cold? Oh yeah, absolutely would be, because that carbon dioxide is bringing a lot of, or it's extremely cold, so it's reducing the temperature very quickly. Now, go back. Yeah, there we go. Good. So this is one of those processes where carbon dioxide as solid is going to a gaseous state. Now, there are different types of intermolecular forces. And this table shows them in increasing strength. And as those strengths increase, physical properties like melting and boiling points also increase. Now, I'd like to draw your attention over here to your weakest of the intermolecular forces. They are known as dispersion forces. Sometimes you might hear these referred to as London dispersion forces, or LDF, or last but not least is van der Waals forces, VANDERWAALS, van der Waals forces. So LDF is London dispersion forces, London dispersion forces. These are forces that every single molecule has. So you could kind of think about this as kind of a hierarchy. This is like the foundational force that every single molecule is going to have. Now, the strength of these forces will vary a little bit depending on their size. Next up are dipole-dipole forces. These are only polar forces. What that means is that if you have a molecule, I'm going to draw, well, actually, I'll make a better drawing. This is the type of force that's going to exist between a positive something and a negative something. A molecule that has a positive charge and a negative charge, that would be an example of a dipole-dipole charge. So these are molecules that have opposite charges that are kind of attracted to one another. Then last but not least, and the strongest of our intermolecular forces that we're going to look at are known as hydrogen bonds. Now, an important thing to know is, and this is kind of tempting, but if I said, hey, CH4, I'm going to draw two molecules here, CH4 and then another CH, H, H, H. Okay, so here's two molecules. And one thing that I want you to see on here is, well, there's a bunch of hydrogens. There's a carbon and a hydrogen. Now, let's go ahead and inventory the types of forces that basically attract these two molecules together. My first question is to ask you whether or not hydrogen bonding is going to attract these two molecules. I'm going to label them A and B. So C, oh yeah, lowercase, or B and then A. Okay, now in order for a hydrogen bond or hydrogen bonding to exist, you have to have a molecule with an OH, an NH, or an FH. Now add to the chat your answer as to whether or not these molecules have an OH, NH, or FH. No, yeah, absolutely. Not an elaborate trick question or anything like that. So now my question is, does hydrogen bonding hold these two compounds together? Also not a trick question. No, you're absolutely right. I bring this up and I want to like kind of let the like awkward moment sit for a second because it's very tempting to be like, oh, hydrogen bonding. I need hydrogen. And to look at CH4, those two molecules there, and be like, well, they both have hydrogen, so hydrogen bonding. That's not the case. Remember, first of all, we're talking about intermolecular forces. So we're talking about this molecule right here and this molecule right here interacting with one another. Now, with this definition, by not having an OH, NH, or FH, these two have no, I'll just label it as no H bonding, no hydrogen bonding. Okay. Next up, we've got dipole-dipole interactions. In a dipole-dipole interaction, we have to have a charge. Now, before I ask you about these, I'm going to show you a molecule, a charged molecule, and how it's typically drawn. So we've got two Lewis structures here. N, H, 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 positive charge there. Okay. So that's how I'm going to draw a charged molecule. Now look at that. Well, actually, heck, add to the chat. Is this a positively charged molecule? Yeah, it is. It's a positively charged molecule. Okay. Um, so if I'm indicating with a positive symbol that that is a positively charged molecule, do you think that I would indicate a negative charge with a minus symbol? Absolutely. Okay. So now with that in mind, do you think that these two CH4 molecules have a dipole-dipole interaction mediated through two charges? And before you answer, do you see any charges on either of those CH4s? No charges, no dipole-dipole. Does that make sense? Okay, great. So now what I'm going to say is no dipole, dipole for these two molecules interacting with one another. Okay, my last but not least are dispersion forces. And remember what I said about, well, everything has dispersion forces. Now here's my question. Do these two CH4 molecules have dispersion forces that kind of attract them to one another? Also not intending to be a trick question, but yes, they do have dispersion forces. So when we look at these two compounds, they do have dispersion forces that attract them to one another. Do they have dipole-dipole? Nope. Do they have hydrogen bonds? Nope. Okay. Now I'm going to give you a couple of other molecules. And I'm going to clear all my drawings here. And so let's go ahead and look at, and what I want you to do is I want you to tell me, and actually we're going to kind of move through this a little bit more briskly. Do these two molecules, are they held together? When you have a chance, can you explain further why it's not dipole-dipole? How to know if it is polar or not? Okay, and okay, so I think that this will probably, let's look at these two molecules and I'll try to answer your question while I'm explaining these two molecules. So when you have a chance, can you further explain why it's not a dipole-dipole and how to know if it is polar or not. Are you referencing the CH4 molecules? I think that you were based on when you probably had to start typing the question. Okay. So, you know what? I'll put these back up. I'll go through those. And then I'll revisit or I'll visit the other ones at the bottom of the page. Okay, so we've got our two CH4 molecules. Now, the hydrogen bonding question, I think, is pretty clear. You just have to ask yourself, is there OH, NH, and FH in both of the molecules? In this, we don't see the FH, NH, or OH. All we see is CH. Okay, so hydrogen bonding is out. And so I'm going to put an X by hydrogen bonding. Now, dipole-dipole. The important thing about this is that these molecules either have to observe a charge or be polar. Now, the question that you're asking, Kevin, or part of your question is, how do we know if it's polar or not? Now, whenever we talk about polarity, polarity is a question of electronegativity differences. So how much does one atom want electrons more than the other? Now, I didn't give you an electronegativity chart here, but you can expect that whenever I had a question about electronegativity on the last test, but my table didn't get copied in there, so I gave everyone credit on that. But when you look at a molecule, you have electronegativity values. So let's say that H has an electronegativity of 2.1, carbon has electronegativity of 2.5. Now, each one of these hydrogens has a value of 2.1. Now, whenever we define a bond as being polar, we want an E negativity difference or a delta meaning change or a difference of electronegativity of 0.5 or greater. Now, I did not give you the values for these, but there's another way that you can determine if a molecule is polar or not. And if we look at this molecule right here, the way that I want to imagine, or let's go ahead and imagine that we're looking at, let's cut it in half right here. And whenever you cut something in half, and it's the same on one side as it is on the other, what's the word that we use for that? I think probably maybe your first art class that you ever took, you learned that term. Symmetrical. Symmetry. We see that it's symmetrical. Whatever is on the left-hand side is the same as what's on the right-hand side. And you can look at it as, okay, they're equal, they're even. That's absolutely right. Now, whenever you have a molecule that is symmetrical, that has symmetry, that molecule is by nature nonpolar. So a nonpolar molecule is a symmetrical molecule. And a symmetrical molecule is a nonpolar molecule. So whenever we look at CH4, I didn't give you the values, but we can kind of cross those out and say we don't really even care about those because of the fact that in every direction, that carbon has a hydrogen outward of it. So that would be a symmetrical molecule. And so when we define this as a symmetrical molecule, we can say that yes, indeed, or sorry, not yes, indeed, but we know that these are nonpolar. And therefore, we do not have a dipole-dipole interaction between these two. Does that sound good? Absolutely. Okay. So did that bring up any questions for anyone else? Okay. So now I'm going to go back. I'll leave the structures for my molecules for my other example. I'll leave those up here. But now what I'm going to do is I'm going to go down to the bottom of my slide. And I'm going to be focusing on these two molecules. Okay. And what I'm going to do is I'm going to give myself H bond, D, D, and DISP. And I'm going to ask myself for each of these molecules, do I have hydrogen bonding? Do I have dipole-dipole, and do I have dispersion forces? Okay. Now, we're going to look at each one of these molecules when we're asking about their interactions. So the first question is, and I always kind of think about this as like the peak of the pyramid, hydrogen bonding. Does hydrogen bonding exist between these two molecules? Okay. Now, in order for hydrogen bonding to exist, we have to have OH, NH, and FH present in both of those molecules. Okay, so my molecule on the right, NH4. Do I have NH? I do. Great. Okay. Do I have OH? Nope. Do I have FH? Nope. Does it matter that I don't have OH and FH in that molecule? It doesn't. Because whenever I'm looking for a hydrogen bonding pair of two molecules that hydrogen bond, what I'm looking for is one of those three in each of them. Okay, so I've got it in my NH4, but what about in my other molecule? Okay, so it's really tempting. I've got an oxygen here, and I've got an oxygen here, and then I have hydrogens over here, but do I have an OH? Sorry, I'm trying to erase the underlines there. Do I have an OH in my molecule on the left-hand side? I don't. So since I don't have an OH there, do I have hydrogen bonding between these two things? Do they both have kind of the minimum tools that they need? They don't. So for this, what I'm going to do is I'm going to say hydrogen bonding. Nope. Okay. Next up, I've got dipole-dipole interactions. Okay. So here what I'm going to have is polar molecules. Okay. And, you know, here it's kind of interesting because what I was just talking about a moment ago was basically like if it's symmetrical, it's a non-polar molecule. But another thing that we want to look for when we talk about dipole molecules is we're looking for a charge and looking for charges. Do these two molecules have charges? Both of these molecules have charges. In which case, what do we want to say about them and their ability to have a dipole-dipole interaction? We would say, yes, they do both have charges, so they can have a dipole-dipole interaction. Mix-up is our dispersion forces. And before we even answer that, one thing that I want to say is just because a molecule has dipole-dipole does not mean that it cannot have dispersion forces. It's not like we only get one of them, but instead, think about them as, well, everything's going to have dispersion forces. Molecules might have dispersion and hydrogen bonding, might have dispersion and dipole-dipole. It might have dispersion, dipole-dipole, and hydrogen bonding. So now to answer this question, do these two molecules at the bottom of the screen, are there dispersion forces that hold them together? Absolutely. Yes. I always kind of think of the dispersion forces as basically like a foundation. You know, that foundation has to be there in order for other intermolecular forces to be there as well. So something might have hydrogen bonding, dipole-dipole, and dispersion. Nothing is going to have only hydrogen bonding because everything has at least dispersion forces. Okay, Now here is, and so actually let me jump back for a second. When we have these higher interactions, like hydrogen bonds, that's where you're going to see strong forces between molecules. And when you see those strong forces, then you're going to have very strong interactions leading to a higher melting point and a higher boiling point. Now, before we get to the next question, which I'm going to show you the question and then I'm going to put it up on Top Hat, these dispersion forces, they vary in strength depending on their size. So if we had CH4, CH4, those two molecules, and we also had two copies of a molecule known as C2H6. The interaction, there are going to be more dispersion forces between these two compounds than between these two compounds, or these two molecules and these two molecules. So the stronger dispersion forces are between these right here because these molecules are larger. There's more opportunities for dispersion forces. Now, with that in mind, let's look at these. We've got a molecule known as methane, which is 1 carbon, ethane, which is 2 carbons, and then propane, which is 3 carbons. Which of these do you think has the highest boiling point? Think about that for a moment. Do not answer it yet because we're going to see this as a Top Hat question. Which has the highest boiling point? Methane, ethane, or butane? And I think that, yeah, I've got set a 60-second timer on here, beginning now. Methane, ethane, or butane? And in the event that you can't answer this, I'll add it as an assigned question. But this is it. If we get 100% on this, 1 bonus point on the exam. The last exam. I'll just add it in. And I'm only going to be counting the answers that go into Top Hat for my question of if everyone gets it right. Methane has 1 carbon, butane has 2 carbons, or sorry, ethane has 2 carbons, butane has 3 carbons. So it follows that trend of A, B, C. Which one of them will have the highest boiling point? Essentially, it's almost a question of which one of these is the largest. I'll add 15 more seconds just to get as many answers as possible to the Top Hat. Okay. 10 seconds. If everyone gets it right in Top Hat, it's 1 bonus point for everyone. I think we're going to do it. Responsive. Close. We'll get them next time. So the correct answer is butane. Methane has 1 carbon, so the dispersion forces between the methane molecules are low. Butane, that's got 3 carbons. Butane has, as the largest molecule, is going to have the highest boiling point. All right. So when we talked about polarity, okay, so in the event that it's not popping up for you, this will be an assigned question. So you want to make sure that you go ahead and do that this afternoon before it expires tomorrow. So it will be on Top Hat as an assigned question later today. So the question of polarity is basically, well, you know, what we talked about, the symmetry of the molecule. So I think what I'm going to do, I think I'm going to go ahead and actually, I'm going to stop right there. We've got a little bit more that we can catch up on Wednesday. I don't want to go too far into or go any further because I think that what I'm going to have to get into after that will kind of extend. So I'm going to go ahead and stop my recording right now.